Welcome to this puzzle session. Here is the puzzle for today. Several football teams enter a tournament, and one of the rules of the tournament is that, and the only rule that we want to concern ourselves with, is that no two teams are allowed to clash more than once. So it is possible that two teams do not clash at all in the entirety of the tournament, but if they clash, that's the only time they clash. They do not clash more than once. So we want to show that at any given time in the tournament, there will be two teams which up until that point have played exactly the same number of games. So a very trivial case would be, as soon as the tournament starts, no team has played against any other team. Then every team has played exactly 0 games. So of course there are two different teams with the same number of games. So of course we are assuming that the number of teams is at least 2, right? Because otherwise it's not really a tournament. Okay, and if suppose one game has happened, exactly one game has happened so far, then you can find two teams with the same number of games, because the two teams which have played a game have played exactly one game, and therefore they have played the same number of games. So basically, so here is the solution. We can represent this data by means of a graph, and you can follow the suggested video flashing at the top right corner of the screen for basic graph theoretic introduction. So what you do is you fix a time, whatever day you want to say, 8th day, 9th day, 3rd day, whichever day. And up until that day, you have the data as to which team has played against which team. So that data we can represent by means of a graph. Here the teams will become dots, or rather the vertices of the graph. And if, let's say, this team has played a match against that team, then we join an edge. And if not, then we don't do anything. So the graph could look complicated. It could be just a complete graph. Every edge, every vertex could be connected with every other vertex, or it could be something like this. And you can see that here you can find two vertices which have exact same degree, meaning that these two teams have played the same number of games. So the connection that one has to make is that the degree of any vertex is the number of games played up until that point by the team represented by the vertex V. So if we follow this, then the problem actually boils down to a purely graph theoretic statement, which is that in any finite graph, there are two vertices of the same degree. So let's prove this, and that will be the end. So suppose not. Then there is a graph G, finite graph of course. Then there is a graph G equals V comma E. V is the vertex set, E is the edge set, such that no two vertices in the graph have same degree. Have the same degree. So let's say there are n vertices, so note that the degree of a vertex can be then degree of a vertex is in this range. Why is that? Because if you fix a vertex V and draw all the other vertex in a separate blob, then even if you connect this vertex to every other vertex, you get at most n minus 1 as the degree of this vertex. So the degree is at most n minus 1, and of course it cannot be less than 0. So it is in this range. Now we have n vertices, and each vertex can have degree in this range, with the further condition that no two vertices have the same degree. It follows that for each I in this set, there is exactly one vertex of degree I. So in particular, there is a vertex of degree 0 and there is a vertex of degree 1. There is a vertex of degree 0 and there is a vertex of degree, I said 1 but I meant n minus 1. Okay, so suppose this is my vertex of degree n minus 1 and all the other vertices I'm drawing in this blob. Then what does that mean? This vertex, since this has degree n minus 1 and there are n minus 1 other vertices left, so this must be connected to everything. But if this is connected to everything, it means that no vertex here has degree 0. And of course this does not have degree 0, which contradicts this inference. So this gives us a contradiction. This is the symbol for contradiction. And we are done. So very simple, very simple proof, but an interesting conclusion nonetheless. So as usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening and I'll see you next time.